To really measure global warming, you have to measure the energy coming in from the sun at the top of the atmosphere, okay? And
Mhm.
then the energy going out at the top of the atmosphere. And if the energy coming in is greater, then you can say confidently that the system inside of that ball, because outside of it, there's nothing, right?
Yeah.
Inside of that ball, what we call the top of the atmosphere, which is like, I don't know, 100 kilometers up or something, right? If the energy in minus the energy out is is greater than zero, right? Energy in minus out, then we have warming. If the energy in minus out is less than zero, we have cooling. If the energy in minus energy out equals zero, we have nothing, right? Well, let me tell you, it's not statistically different from zero as far as we can measure it right now.
Yeah.
And anybody saying that it is lying.
Jonathan, thank you for joining me today. We spoke a couple of months ago, and you went through some of your arguments. You'd written a paper with Grok 3 in order to explain your views on climate change and your criticisms of some of the assumptions behind that. So, can you bring us up to date as to where you are now and what you've been doing since that time?
Well, I've been doing a lot of different things, but what I wanted to talk to you most about today is the subject of what everybody thinks they know called global temperature. And the um, the problem with it is that it's what everybody thinks they know about global temperature is completely wrong. Put it that way. Let's
I'm
start
not so
there.
sure that people understand what temperature is anyway. I mean, I was quite surprised. I mean, I've done physics. I've done an undergraduate and a postgraduate degree in physics. And it was only at a certain point during that time that suddenly the light bulb went on that, hey, there's a difference between temperature and heat. I think for me, that light bulb moment was when someone told me, you do realize there is more heat in an iceberg than there is in a cup of coffee,
Right.
um, because there are more molecules in the iceberg. And you realize that, oh, yeah, the total amount of temperature is the total amount of jiggling of all the atoms, all the molecules in the ice cube and in the cup. But temperature is a different matter. It's not the total amount of energy.
No,
The
temperature is not
average,
it's
it's
not
the
energy,
average
and
amount of kinetic energy or related to the average amount.
it's related to the average amount of kinetic energy. And what people who haven't taken thermodynamics, which is 99.9% of the planet, is it is not, people often say it's a measure of energy. No, it's not.
No.
Okay. You can't get energy from temperature.
Heat is a
Temperature,
measure of energy,
heat
but
is
temperature is a measure of the average speed or kinetic energy
it's
of
and
the
even
molecules.
there, it's only defined in a system that is in equilibrium. In other words, if you have a set of molecules that are rapidly changing in their speed distributions, there is no temperature. Okay? People don't understand this. And furthermore, the kinetic definition of temperature is not actually the definition of temperature. It's another thing people confuse, even physics majors, even PhDs in physics, and virtually all climate scientists who don't understand any of this, is that temperature is only defined in equilibrium. So, what does that mean? When everybody thinks they know what temperature is because they have a thermostat and they have a thermometer. You can stick the thermometer up in the air and measure a temperature. That only measures the temperature at this one tiny little point in space, where that little volume of space around the bulb of the thermometer is in what we call a pseudo equilibrium. It's so small that, unless you're in the middle of the sun or something, it's probably not changing very much at all. In other words, it's in equilibrium, okay? But then the problem happens when you try to put together temperatures that are from different parts of a non-equilibrium system. What's a non-equilibrium system? Like the room you're in right now. Okay, if you take the temperature in your room next to the window, and then the temperature in the glass of ice water on your desk, and the temperature next to the heat vent, they're wildly different.
Yeah.
So there is no temperature. Even in your room, there's no temperature. Okay, there's no global average temperature of a room.
Well, let me unpack that a bit. So um, there is a temperature at each local position, and the the temperature which you measure in one place could be different to a temperature in another place, and usually are, because of they're in different locations. So the
Right,
question then becomes, can't you just average those two
right,
temperatures, say?
right. And so that's the next question, which comes about from people again who don't know thermodynamics, which is almost everybody in the world. So the short answer is no, you absolutely cannot. And here's why. Temperature is what's called an intensive property. It's
Yeah,
like pressure, it's like chemical potential, and it's not additive. You can't say, well, it's 10 degrees over here and it's 10 degrees over here, and therefore it's 20 degrees. You can't do that. Okay.
no.
It's not additive because it's not a measure of an amount. It's a measure of a state. And people don't understand this. The state, if you think of ideal gases, the definition that most people know of temperature is the one where we say it's a measure of the average kinetic energy of the molecules. Okay. Even that is an imprecise, incorrect definition because it doesn't measure energy.
So we're not talking about the total heat of the Earth when we're talking about a temperature.
No.
We're talking about some other abstract concept, really,
Correct.
which has
Correct.
some kind of a connection, but it's not very clear what that connection
No,
is.
it is very clear, and it's very clear that an average temperature has no connection. But
Yeah,
let me the way you get from temperature to energy is you have to know two other things. You have to know what's the mass, and you have to know what's called the heat capacity.
yeah,
The heat capacity of a substance tells you how much energy it takes to raise the temperature of that thing to an equilibrium by 1 degree, right? 1 degree Kelvin, I think, is usually what's done. So if you know, and then you got to know the mass because, as you pointed out, the amount of energy is proportional to how much of the stuff you have, right?
yeah.
So, to calculate energy in the Earth's system, you would have to, at every point in space, measure what's the mass or the mass density if you were doing an integral, what's the heat capacity at that point, and what is the temperature at that point. And then you could integrate that theoretically. Of course, there's no physical actual way of doing this. We don't have
Yeah,
instruments everywhere, yeah, et cetera.
yeah.
But that would be the mathematically correct calculation of the energy in the atmosphere.
Okay, well, people don't bother with energy; they just bother with temperature. And what they've got is a whole pile of thermometers, temperature measuring devices, whatever they may be, scattered all around the surface of the Earth. They even have some satellites which look down as well. And they say, oh, look, the temperature in Alaska at the moment is quite cold. The temperature in the Sahara Desert is quite hot. Let's just average those together and we'll come up with a figure which, taken from all the way around the world, will give us the temperature of the Earth. What's wrong
Right.
with that?
Okay. So people think if you have a set of numbers, let's average them. That's a natural tendency.
Yeah.
If you got a lot of numbers, do statistics, right? That's what you learned in statistics class. So numerically, yes, you can take the average of any set of numbers. But the jump that people don't get is not all averages are meaningful in the real world, adding the clause in the real world. Now, why is that? Let me just give you a very simple example. Telephone numbers are numbers. They're meaningful numbers. Okay. Each telephone number, if you dial it, gets you right to a person. It's a perfectly meaningful number. If you take two telephone numbers and average them together, do you get another telephone number? No. Okay. So the exact same principle applies here. An average of two temperatures in a non equilibrium system is not a temperature. It's not, I'm not saying it's a category thing. It's logic. This is so fundamental that people don't get it. It is a category error to call an average of two temperatures of a temperature because it's not,
Okay, let me
because they're not
tell you.
additive in the first place.
Let me give you an example, a counter example which I think people might consider much more intuitive as to why you should be able to do this.
Okay.
I've got a glass of water here, and the temperature of the water is 20 degrees.
Okay.
I've got another glass of water here, and the temperature of the water is 40 degrees. Now,
Okay.
as you say, it's an intensive property. When I mix those together and put them together, I'm not going to get 60 degrees, but I am going to get the average, and the average will be halfway between. They'll be
Wrong.
30 degrees. You mix the two
Wrong.
glasses of water, 20 and
Wrong.
40 makes a 30. So
No,
isn't
that's
that
wrong.
exactly what's taking place when you're averaging temperatures around the world?
But what you just said was incorrect. When
Ah,
you when you add two glasses of water together, you do not get the average temperature of the two.
you don't?
No, absolutely not. The point
Um,
is that's not the case with the Earth. The Earth is a system where when they first of all when NASA and IPCC who created this fraud purposely created this fraud, and I'll show you that as well here.
the
Um,
fraud being
the fraud being that global temperature is physically
meaning,
totally meaningless.
yeah.
And they and not only do they say it's meaningful, they use it as the root element of every single one of the conclusions that you know of. In other words, if I ask you anything, tell me something you believe about climate change, I can show you that the root element of the proof of that statement that you believe in, which is a falsehood, is this global surface temperature fiction. Tell me something you've heard that you
Well, look,
believe.
look. Let me put it this way to you: that why temperature becomes something which is intuitively apprehended by people. We know from historical records that the Earth has gone through periods of cooling and warming and cooling and warming. We've had, I believe, something like 11 ice ages where glaciers moved south and then they retreated again.
Yeah,
Now, the Earth has gone through. You'd have to say that the Earth was colder in an ice age, and it was warmer in a warm period like the Middle Ages. There were times when the Thames in London would freeze over and they could hold a fair on it. And there are times today when you can't do that. So
right.
there must be some number or some figure or some parameter which indicates the difference between those two different times. And that
Absolutely.
difference, that parameter, we're using as a shorthand as temperature.
Yeah, but it's not temperature. That's the problem. That's the fraud. There
Well,
is a
what
number.
is
There
it
is a
then?
number. It's
If
very
there is a real
simple.
difference, though, what is the difference if it's not temperature? Because if you do have an ice age where it's much colder, and you do
Right.
have a warm period when it's much warmer, there is that difference. And there must be
That's
some way
right.
of describing it,
There is. It's
some
very
kind of
simple.
numbers in a quantitative way.
There is. It's very simple.
Yeah.
Yeah. It's called energy.
Ah,
Okay. So when they're not actually ice ages, they're glaciations, is what you're talking about. We're in an ice age right now. In fact, anytime when there's ice at the poles, that's called an ice age in, you know, paleoclimatology. Um, so we're in a 2.5 million year old ice age right now. And during that ice age, we've had many glaciations where, like you said, we've had ice come way down south and then go way
yeah.
back up north, and the sea level changes dramatically because that ice is basically was seawater. It gets sucked out onto land and then et cetera. So, and what causes that is a large change in the energy that is coming into the Earth system from the sun. All of the energy, virtually all of the, I mean, by many, or 6 or 7 orders of magnitude larger than any other energy source that drives the Earth's climate system is from the sun. Okay, it's something like 10 to the 27th, as I recall,
Yeah.
joules. Okay, it's a huge number. And if you add up all the radiogenic and geothermal energy that comes from inside the Earth, it's, you know, a million times smaller, so maybe 6, 7 orders of magnitude smaller. But the point is, all of the energy comes from the sun. So what happens when those glaciations occur is we suddenly, and suddenly in geological terms, means every 10,000 years or so, right? We suddenly get a lot more energy coming from the sun. And why is that? Well, there's a guy named Milankovitch who discovered and figured out the issue, which is the Earth changes its angle towards the sun gradually, not by a huge amount, but by a couple degrees. It also wobbles. It has precession. In other words, it's like a top. It kind of wobbles around like this. And if you point the Earth more towards the sun, what happens? You get more heat because the rays of shortwave energy are impacting the Earth more directly. You think of it this way: if the rays are skimming across the top, you're not absorbing any of it, right? And as you tilt towards it, you get more and more of it. So a small change in the tilt of the Earth, which happens every 40,000 or every 100,000 years, causes a massive difference in the amount of solar energy coming into the Earth system, which causes what you're talking about. Now, but that's a whole separate issue. Temperature doesn't measure. Even during glaciations, there are parts of the Earth that are still warm. So the question is, and if you average together, I'll give you an example how they calculate this fictitious global temperature average. They average together sea surface temperatures, and then they average together air above land temperatures, and then they average those two together. Now think about this for a minute. If you wanted to claim, as they fraudulently do, that somehow this magical average of temperatures, which is not a temperature, um, somehow indicates energy in some way, which is what they claim fraudulently. Think about this. The density of water, seawater, I'll just talk rough numbers here, right, is about 800 and something, 30, 40 times greater than the density of air near the surface of the Earth. Okay. And the heat capacity, again, rough numbers, is about 4 times greater than the heat capacity of air, rough numbers. So 4 times 830, let's say, is like 3,400 times, 3,000. So it's more than 3 times greater energy in any given volume of seawater than in the same volume of air.
Yeah. Yeah.
Okay. So if you say, I'm going to just look at temperatures, I'm not going to look at their density or their mass or their heat capacity, you're now saying a 1 degree rise in some seawater is weighted equally to a 1 degree rise in air. It's off by a factor of 3,000. It's not even in the same universe. It's 3 orders of magnitude wrong. So it can't possibly represent energy just by that one argument alone. I was at this conference a couple of weeks ago with John Clauser, who was the 2022 Nobel Prize winner in physics. Brilliant, brilliant guy. And I was sitting next to him, and we were talking about a bunch of different things. And I used one of his quotes about the fact that, science is about observing nature, seeing what's happening in the real world. That's what science is. Um, and he said something even better when we were sitting at the table together. So I said, John, I'm going to add this into my talk right now. Is that okay? He said, yeah. So he said, theorists talk to each other and experimentalists talk to God.
Mm.
I love that line.
Yeah.
So, and so his point was um, that when you're a scientific theorist, you're saying, I think the world works this way. You come up with some hypothesis, as we call it in science, just a theory, right? And then you go out and you do experiments and see if you can disprove the theory. Remember, you can never prove a theory in science. In fact, if you could prove it, it's not science, right? An hypothesis has to be falsifiable in order for it to be a valid hypothesis, right?
Yeah.
That's the basic element of science. So in science, we're never dealing with absolute truth. We're just trying to get closer and closer and closer to truth, which is why he said we're talking to God. Experimentalists are talking to God because we're trying to figure out what God did in creating this universe, how he created it. And God's given us science to try and figure it out. but only he knows the total truth, right? So that's kind of what he was saying, right? So but mathematics is different. Mathematics is, in a way, some people, that's why some mathematicians say it's kind of like God, because it is absolute truth. It existed before we thought of it, and it will always exist. So, what I'm saying about global temperature is in that category. It's a mathematical proof. Now, it's been known by people who understand thermodynamics since the 1880s. So I did some research and said, well, why is it people haven't talked about this? Well, there's a bunch of reasons. Turns out that the smart physicists like Einstein and Bohr and Planck and those guys, they were worried about much bigger, more complex problems, quantum mechanics and building the nuclear bombs and, difficult stuff, right?
Yeah.
And nobody was interested in climate science then. They just had weather reporters. There was no climate science, okay? So the first thing they started doing was they put up thermometers everywhere and tide gauges everywhere. And that's what weather people did. They monitored thermometers and tide gauges. And it's perfectly valid to monitor thermometers and tide gauges and whatnot on a local basis, right? It's one
Yeah.
place. It wasn't until around 1930s when a guy named Guy Callender, who was a steam engine engineer, decided to start averaging these numbers. And he knew the physics of steam engines, but the problem is the thermodynamics of steam engines is all equilibrium thermodynamics. It's not non-equilibrium. So he had never thought about the problems of non-equilibrium thermodynamics. The surface of the Earth is wildly non-equilibrium. What does that mean? Well, you got temperatures that range from negative 80 degrees in some places, I think, centigrade, or you could turn that to Kelvin if you want, but and as high as 40 something degrees, 45, 50 degrees, I think so,
Yeah.
right? So that's what, 130-degree range of temperature, okay? And then you've got the difference between pressures of the air at different altitudes or the water, the mass density, the density difference, and the heat capacity differences. And then you've got massive humidity differences. At the Antarctica, the air is like zero humidity, and at the equator, you got heavy humidity, right?
So let's try and
This
pin this
doesn't
argument down
exist.
a little bit more tightly, so at least I can get it clear in my head.
Yeah,
Global temperature is fictitious. That's the
completely.
claim. Okay. But people say, well, wait a minute, we've got temperature stations all around the world. If we add them together and average them, they all measure temperature locally.
Right.
And if we average all the local temperatures, then the implication is, or the argument is, we therefore get a global temperature. You're saying it's not right. So what's the key point?
Temperature is an intensive property. It is not
Yeah.
additive and it is not averageable. When you add two temperatures together, you don't get a temperature. If you
Right.
add three temperatures together, you don't get a temperature. If you add three temperatures and divide by three, it's not a temperature. It's nothing. It's a category error. It's a fictitious number that has no physical meaning whatsoever.
So wait a minute. The I gave you the counterexample earlier on. Two glasses of water, two different temperatures, same in every other respect. When you mix them together, you get some temperature which is in between the temperatures. Now, it may not be linear, it may not be a strict average, it may be a harmonic structure, but the averaging of in some form takes place because those two temperatures convert when you join them together, and presumably there's a mathematical formula which, if you get it right, will tell you what the combined temperature would be. And that would be the equivalent of mixing together local temperatures to make a global temperature. What's wrong with the argument?
Because it's not the equivalent of mixing local temperatures to make a global temperature. You're talking about an extremely simple,
Yeah.
limited system where you mix two identical things together and you're going to get some temperature in between the two temperatures, but even that will depend on the composition of the two substances, the heat
Okay.
capacity, the heat
So
flows, everything.
your point being is that what we've got when we're trying to gauge temperatures around the world is a whole pile of um, non-homogeneous things,
Not only
water,
non-hom
seawater, gases, clouds, humidities, all of them, they're non-homogeneous. They're not the same kind of thing.
they're not
And
only non-homogeneous, they're massively separated. There's no such thing as thermodynamics at a distance, right? In quantum mechanics, entanglement tells us that there's quantum things that happen at a distance. There's no temperature at a distance, and there's no thermodynamics at a distance. And a piece of ice here does not melt because it's hot over there. The only thing that'll make a piece of ice melt here is if it's hot here.
but we don't have that kind of
No, we have a turbulent system of essentially think of it as boiling, not boiling in the sense of hot, but roiling, let's say. We
yeah.
have a turbulent, roiling atmosphere, a turbulent, roiling ocean, okay? And the earth is spinning, right, which causes things to move. And then the energy from the sun is coming in, and as the earth spins, it hits this side, then it hits that side. When it's hitting this side's getting energy. When it's faced the other way, it's not getting energy. So the energy fluxes are going up and down by massive amounts, and everything is moving. And that's why we have a climate system. Okay, it's because there's massive gradients all over the globe.
Okay.
Okay, so you can't take a temperature. If, by the way, what I'm saying is obvious from first principles of thermodynamics, but it was also rigorously mathematically proven in a paper by a friend of mine, Christopher Essex, who's one of the most brilliant mathematicians in the world. And he and Ross McKittrick and another scientist named, mathematician named Bjarne Andresen from the Niels Bohr Institute in Copenhagen, uh, wrote a paper in 2007 proving everything I'm telling you with rigorous mathematics. It's a 40-page mathematical paper. Okay. First of all, they note, first of all, that temperature is not additive, and therefore there's no, not only is it not averageable, if you, there are occasions where you can take a set of data, and so you're not sure about the, in this case, we're totally sure that an average of temperatures is not temperature. So if it's something else, you've got to prove what the relationship is. Nobody's even proposed a possible relationship because there is none. And this paper goes through it. But the choice of averaging method is arbitrary. So in other words, if I'm averaging resistance in a circuit for the electrical engineers out there, and I've got a resistor R1 here and R2 here, and I put them in parallel, and then have this circuit. What's the resistance of the circuit? The resistance of that circuit, if you learn your electrical engineering, is 1 over R1 plus 1 over R2. That's called the minus 1 Hölder mean. There's a whole set of averages based on the power of the thing that you average. So x to the, if you average the x to the minus 1, that's this one I'm talking about. If you average other things like kinetic energy, you use a different type of average. If you average radiation energy, you use a different type of average. So if there's a physical principle that dictates how you're supposed to calculate something, then there's a particular averaging method. But in the case of this, since there is no global temperature, there's no such thing as a global temperature for a non-equilibrium system. There's no temperature of any non-equilibrium system. Temperature is only defined in equilibrium. So there is no temperature. Then what's the chosen averaging method, and why did you choose that averaging method? Since there is no choice of averaging method, it's arbitrary. And therefore, when you actually take actual data and use different averaging methods, you get different numbers with different slopes. In fact, some averaging methods have the slope going up, and some have it going down, some have it staying the same with the same data. Now, since the choice of averaging method is arbitrary, the result you're getting is what's known as a statistical artifact. It's just a made-up human choice.
Hmm.
So if you get a result that says something's going up because you chose that method of averaging, it's meaningless because someone else could choose another averaging method, and you have no reason You have no way of proving that his averaging method is not more correct than yours. So the averaging theorem that he proves a whole theorem about the averaging theorem. He then takes the actual data, by the way. He takes data in this paper from, I forget, 7 or 10 or 12 weather temperature stations, and then averages them together using 4 different methods of averaging and show, or 3 different methods, I forget. But anyhow, he does it with different methods and shows that in one method it goes up and another method it goes down. So depending on how you chose to calculate your average, you decide it's warming and another guy decides that it's cooling. And so the question is it warming or is it cooling? And the answer is it's both.
Yeah.
It's
No,
not
I,
determinable. In fact, and then he has another theorem that he proves, and in this paper there's about 10 different theorems that he proves, which is why it's called the overlap theorem. If you have a temperature field where any of the temperatures overlap with any of the others that you want to compare it, you want to say, is this thing colder than that? The only way you can make a meaningful statement about whether something is colder is if there's no overlap. So, in other words, if all the temperatures in one set are greater than all the temperatures in the other set, then you can say this temperature set is warmer than this one. But if the temperatures are not all greater, you can't say that because there's an overlap. And because you're only talking temperatures here, you don't know how much mass is associated and how much heat capacity is associated with those temperatures. So even a small overlap, even if the overlap looks like it's going to the right, it might go to the left, depending on how you average it.
yeah.
Okay.
I can understand what you're saying there, but isn't there a way around that
No.
by by not taking absolute measurements of temperature, but differences, anomalies? You average temperature anomalies. In other words, as the temperature changes, you look at only the changes over, a week, a year, or whatever it may be. And it's those differences in temperature which then get averaged. Isn't
Right.
that what's taking place in when they're measuring these grand temperature differences?
Again, you might think that if you don't understand mathematics, but Essex thought of that and already proved it. And so the
All right.
answer is no. There's absolutely no difference in the theorems as a result of using anomalies versus temperatures. The
Okay.
mathematics is exactly the same. There are things called there are these things called coordinate transformations, technical terms in math. But anyhow, the short answer is no. The anomalies does not change the fundamental math at all. Zip
Okay.
zilch none.
Let me put another thing to you then, and that is that this global mean surface temperature value, which is commonly used now, is it not justified by the fact that correlations are seen against the variation of the global mean surface temperature? So they look at the amount of carbon dioxide, they look at the global mean temperature, they say, oh, look, there's a correlation between those two. In fact, they go some further to say there's a causation between the two, that as the global mean temperature varies, or as the carbon dioxide varies, the global mean temperature varies. And isn't the correlation, therefore, a justification of the use of that value, no matter how obscure its origins might be?
So, first of all, again, the premise of your question is wrong. So I'll start with that. There are no correlations, number one, no valid ones. Now, uh, all of these arguments, by the way, I've been through, and I've had actually both Grok and Grok 4 and Claude 4 write up papers on this subject and do extensive research on it, which is why we're going to come out with a paper. But there are no published studies, none, zero, okay, that show any actual correlation between this number and the other. And but let me take a step back from that. There are Correlation is not causation, as everybody knows, right? But Spurious correlation is totally meaningless. Now, what does spurious correlation mean? If you have a grandfather clock that is completely dead, not moving, okay? Not moving. It tells the correct time twice a day. You say, well, it's not very accurate, but we know it's exactly right twice a day, so there must be something there. No, there's nothing there. So that correlation is a spurious correlation. So now, if you make up a number, and by the way, you engineer this fake statistic so that it goes up very slightly, which is exactly what they did, right? So it's an engineered meaningless statistic, and it goes up slightly, and then you pick something else in the world that went up slightly, and now you say, look, it's correlated. That's a spurious correlation. First of all, this is a fiction, so any correlation it has with anything is by definition spurious because it doesn't exist. All right?
There is, and so I just throw this in, there is a fantastic website out there. I think it's called Spurious Correlations,
Right.
which just puts up many, graphs of two things and showing a weird, unwonderful correlations that cannot exist, like the amount of seaweed washed up on a beach
Right.
compared to the number of fashions that have been
Right.
presented in Paris. And the correlations are very clearly displayed in the graph, but you can play with the various different settings, but they show spurious correlations, which
Right. So there's a mathematical correlation in the numbers. This is
yeah,
where you go back and forth from numbers to physical meaning, right?
yeah.
Numbers can have correlations with each other, like you just said, all kinds, right? That doesn't mean that one causes the other, doesn't mean they're even related in any way. And if one of the two things is a fictitious imaginary thing that has no physical meaning in the physical world, any correlation that it has is also meaningless. Now, that said, um, so these correlation, when you see people talking about the correlations, you can go search, you can do a deep search, and then you'll find one or two or three papers over the last 50 years that attempts to try and correlate GMST with something. And when you read into the paper further, what you discover is it's a circular argument
Hmm.
that the thing that they were correlating with was a model which was based on GMST, okay, tuned to GMST, calculates GMST internally, that drives other thing in the model, and then they say, look, this modeled result correlates with GMST. Oh, it's called circular reasoning. Okay.
This global mean surface temperature, GMST, is being used quite heavily today to set targets for countries and for governments to meet. So what's the conclusions from that then?
The
Where
most common ones you hear are global warming of 1.1 degrees C above 1850 to 1900 baseline. In fact, that's their big number one conclusion. So right away, that's purely the GMST number. So that statement, global warming of 1.1 degrees C, there's already four lies in that phrase. Why? They defined global warming. IPCC defined global warming as an increase in GMST. Now, as we know, that's not what global warming is. Warming, we know from thermodynamics, is an increase in internal energy. Energy, not temperature. So you can't say global warming and temperature in the same sentence, okay? If they wanted to talk energy, they could, but they didn't. They specifically defined warming as increase in temperature. Then they said 1.1 degrees C, but wait a minute. The 1.1 is not a temperature, it's a change in GMST, which is a statistic which we know is not a temperature. Calling it degrees C is a category error, and it's a purposeful lie because they want you to believe that it's a temperature. It's not. It's a change in this statistic that they calculated. Okay? A change in a statistic which we know does not represent either a temperature or an energy or anything in the real world. So they said global warming of 1.1 degrees C. It's not degrees C. It's not global warming because it's not energy. and the 1.1 is a meaningless number. Okay, so that's number one, right? I'll just give you a couple other ones quickly.
Yeah, we would. Go ahead.
Temperature attribution, all human attribution of changes, that's all based on GMST, all falsified. The projected scenarios, what you're talking about, the Paris Agreement, it's called 1.5 degrees C. Again, degrees C is a lie. Everywhere where they use the terminology degrees C next to a GMST number is a lie. And it's not an accidental lie, it's a purposeful, intentional lie because they want you to believe, and you do believe, everyone believes, that it has something to do with temperature. And it doesn't. Okay. So it worked. It's propaganda at a scale never seen before. Let me give you a few more, and I'll point you to a paper I wrote about this. Um, Rate of warming acceleration, regional temperature change, climate sensitivity. Climate sensitivity is an entirely fictitious thing. Okay. Have you heard of climate sensitivity?
No.
Okay, so this is one of the parameters that they wanted to calculate in the models. And they said, look, if we double the amount of CO2 in the atmosphere, how much will the
Right.
global temperature go up?
Yeah.
Right? So they made an assumption that the global temperature change, delta T, should be equal to the um, the change in forcing due to the increase of the CO2 times this thing lambda, which is the climate sensitivity.
Right.
Okay. That's an assumption
Yeah.
that, but you can see in that equation is delta T equals lambda times F, the forcing, or delta F, right? And so if GMST is a fiction, what does that tell you about lambda? Now, delta F is something that you can really calculate based on some real physics. Now, the so-called forcing number, we
Yeah.
know because we know if you add carbon dioxide molecules to the atmosphere, we know from radiation physics, and there's lots of great measurements about this. These are real measurements, right? You can calculate how much of the radiation of infrared that comes up from the Earth's surface gets re-radiated back towards the Earth versus how much gets sent out into space. And we have very accurate measurements and very accurate experiments that confirm that. So that delta F number,
Mm.
while it's still fuzzy and we can't say what it is
But that's
exactly, it,
it's a non-linear issue, I should think here, because I remember Will Happer telling me that the more CO2 you put in, you might reach a ceiling, so that no matter how much more you keep adding, it's not going to make any difference. It's like when you paint a window with black paint. You know, if you're going
right.
to paint it again with black paint or again with black paint, it makes no difference. The light's still not going to come through. So
Right.
you
It's not that it makes no
calculate.
diff. It's not that it makes no difference, but it's diminishing returns. It's logarithmic. And Will Happer,
Yeah,
by the way, is one of the most brilliant scientists in the world. And everything he says, I listen very carefully. I've never heard him be incorrect about anything.
yeah,
And so he knows all about this. And by the way, he has the best model in the world for measuring the radiation of energy up to the satellites. And he measures them at the satellites, and he has a model for calculating it. And when you look at the output of his model and what the satellites measure, it's like virtually identical. It's unbelievably accurate. So
yeah,
he understands radiative physics better than anyone in the world. And and what he's saying is that the relationship is logarithmic, which means it doesn't cut off, but it gets flatter and flatter. It's a curve that goes up rapidly at first, then gets less and less. And so what it means is, like what he's saying, you get a saturation point where beyond a certain point you barely notice any difference. And we're already at that point. We're at the point where if you double the CO2, the forcing only goes up by a small amount.
yeah.
Okay. And so, and the amount that could possibly change anything again is even smaller. So, but the point is, if GMS, this number that they believe in called sensitivity, is directly related to GMST. So if GMST doesn't exist, the whole theory of climate sensitivity goes away. temperature extremes analysis, sea level rise projections, Arctic warming, carbon budget calculation, literally all of the important conclusions that are used in the media and the policies and the governments and the promotions and everywhere for making laws and this and that and the other thing are all completely undermined by this one absolute truth. Okay. Now, there are things in climate science that are real, like energy and direct measurements of stuff. But for example, you can say, how many days was it over 90 degrees this year? And versus other years or every year. Say each year, how many days was it over 90 degrees? That's not an average. That's what we
would that be a better measure?
What's that?
Would that be a better measure? Would that be a better way of doing it?
Oh, absolutely. That's a very valid measure. And you know what it shows?
Yeah.
It's
Well,
going down. That's why they don't talk about it, right?
that's why they don't talk about it. Jonathan, we've run out of time today, but last question for you would be: what's your attention being focused on next in this area? You've looked at GMST. Have you got a different topic which you're moving towards?
To really measure global warming, you have to measure the energy coming in from the sun at the top of the atmosphere, okay? And then the energy going out at the top of the atmosphere. And if the energy coming in is greater, then you can say confidently that the system inside of that ball, because outside of it, there's nothing, right?
Yeah.
Inside of that ball, what we call the top of the atmosphere, which is like, I don't know, 100 kilometers up or something, right? If the energy in minus the energy out is greater than zero, right? Energy in minus out, then we have warming. If the energy in minus out is less than zero, we have cooling. If the energy in minus energy out equals zero, we have nothing, right? Well, let me tell you, we've had those satellites that do that top of atmosphere measurement.
Yeah.
They've been up for 20 years now, which is not very much time. They started in the late 90s. We have other satellites that went up in 79, but the ones that are measuring top of atmosphere have only been around for about 20 years. And if you look at their in and out measurements along with their uncertainty ranges, because whenever you have a measurement, you have an uncertainty range due to the statistics, but also due to the device that you're doing the measuring with. Okay. The uncertainty range for the outgoing, especially even more than the incoming, is huge. It's like on the order of 10 to 15 watts per meter squared. And what the IPCC hypothetically says, and it's a completely fictitious made up number, but they claim that the energy imbalance is 0.7 watts per meter squared. But we know the measurement in minus the measurement out, okay, is plus or minus 10 to 15 watts. In other words, it's not statistically different from zero as far as we can measure it right now.
Yeah.
And anybody saying that it is lying.
Jonathan Cohler, thank you very much indeed for a very thorough explanation of the climate issues today. Thank you.
You're very welcome.